Okay, now we are again looking at something today that I am doing every single day and perhaps every single hour of my working life. Even now, as I talk to you here it is 5, is busy computing something for my project that we have in the group that uses finite difference approximations to differential equations. The reason for that is humans are not terribly good, and symbolic processing software isn't terribly good at solving things analytically, particularly when they come from real life, because precious few things in quantum mechanics are actually soluble to begin with. Those things that are soluble are next to useless. And we are faced more often than not with differential equations and PDEs that we plainly cannot analytically solve. There will be cases when the function that you have isn't actually a continuous function, it's measured at some discrete points, we've seen the interpolation already, and then we must solve differential equations with respect to those functions. And sometimes it's fairly extensive, right? In various aerodynamics calculations, you would have millions and billions of data points in 3 dimensions around some aircraft running in what the simulation considers to be real time inside it, and turbulence and other such effects, diffusion, chemical kinetics in every pixel of that calculation, because of course at very large velocities, nitrogen, for example, starts oxidizing. And so we have colossal systems of complicated differential equations operating on functions that are not analytically different. In a very simplified form, what we will have is something like this. There will be a coordinate x, there will be a function f of x, and we would like to differentiate a function that is only defined for us at discrete points. So this would be x1, 2, and so on, x k plus 1, and so on. And at these points in here we have f of x1, f of x2, f of xk, f of xk plus 1, these are the values that we do know, and we make a reasonable assumption that the function is well behaved, that is smooth and differentiable, and it doesn't contain a lot of noise in it. How would we possibly differentiate something like that if we don't know what's happening in the middle? Well, we can of course differentiate it approximately. We can say, all right, let's remember the definition of the derivative. It was the limit delta x going to 0 of f of x plus delta x minus f of x divided by. Well, let us say that the stepping of this grid that we have here will be our delta x. Then we can turn that limit expression, if delta x is not infinitesimally small but is instead finite, we can say, okay, we can perhaps approximate this by f of x delta x minus f of x over delta x. And you've seen that a few times already. We have used this approximation when we were discussing, for example, the rules of differentiation. So I used that to prove the chain rule and the product rule for it. All right, so we here have f of xk. We would like to know at this exact same point f prime of xk. And let us use that approximation. So our f prime of xk will be approximately equal to the value that has been incremented by delta x. So the next point, xk plus 1, xk plus 1. Minus the original value, xk, divided by xk plus 1 minus x. So essentially delta x. This is called a finite difference approximation. Finite In the case of one-dimensional function, this is a finite interval. In the case of a two-dimensional function, we have a finite area, something that is colloquially known in computer science as pixel. If we have 3 dimensions, this will be voxel. It's used in MRI, and in n dimensions, it will be just a generic volume element. Engineers are using not finite intervals, but finite elements. To them, these are little springs. And these finite element analysis is done, for example, every time before a building is built or a bridge is set up. Nobody ever does anything experimental these days, including the organic chemists, until they've done these kinds of calculations. What is important about these things is this approximation sign. We really don't want this to go horribly wrong. And it would go horribly wrong if, for example, the interval is too wide or the function is changing too rapidly. So it's not just that we would like to have such methods for calculating derivatives, we would like also to have strict accuracy control over what we do. And therefore we must not only produce such expressions, we must also estimate their accuracy. And that's perhaps the primary topic for today. So let us take this expression in here and try finding out what the accuracy is. Well, we know nothing about the function, save that it is differentiable, and we know nothing about this x and delta x, save that delta x is probably small relative to x, because our grid should be sufficiently fine to discretize the function adequately. So the only thing we know here, therefore, is that delta x is a reasonably small number, and of course, as soon as we know that, we know what is applicable, and that is the Taylor series. Our f plus delta x will be, as we have seen, if we treat delta x as a variable and x as a reference point, and this will be f of x plus f prime of x divided by 1 factorial delta x plus f double prime of x over 2 factorial delta x squared, and so on. And we did analyze the residuals in here, the remainders. We can say that this is of the order of delta x here, when delta x is close to 0. Okay, well, this is quite useful because it allows us to actually replace this, and then we can put it here. F of x will actually cancel, and let us see what we get out of that. So, our f prime of x is approximately equal to f of x plus f prime of x delta x plus 1/2 f double prime of x delta x squared plus order of delta x cubed minus the original function f of x divided by delta x. Well, f cancels here, this one and this one. Then we will have our f prime of delta x. This one's approximate, this one's exact. And so when we write that down, its equation 4 in your handout, we will have, so this should be, right, f of x when we choose this point here, okay, plus delta x. So as per the Taylor series, f of xk plus f prime of xk delta x. So I'm simply repeating what I've got here. This is analytical at any point. This is at the specific point xk. And let's say that this is just order of delta x. So I'll shorten the expression. How can we turn this into the expression we've got there? Well, clearly what I simply do is I take that and solve for it. I move f of xk over here, and I divide by delta x. So f of xk equals f prime of xk times delta x, and we'll divide delta x out. So delta x equals f prime of xk plus something of the order of delta x squared. So far so good. Let me move this number over here. We don't need to change plus into minus because this is just some number of the order of delta x squared, either positive or negative. So the final result, actually let me not divide by delta x first, like that, delta x in here, because we'll have to discuss a little bit more. So our f prime x k is f of xk plus delta x minus f of xk plus order of delta x squared. Right, so to complete our definition of the derivative was this minus this divided by delta x. We need to divide by delta x. This is order of delta x squared. If I divide this by delta x, it will be order of just delta x. So, f prime of xk is f of xk plus delta x minus f of xk over delta x plus something of the order of delta x. And this is what we now need to take a careful look at. So let me just retrace my steps through the procedure because it is a bit obscure. We have this definition of the derivative from our textbook. It's the limit. We've used it many times. An approximation will be when we don't take the limit, when we have finite delta x. Well, to make progress with this, we expand this in Taylor series. If we were to do that, f of x plus delta x is just a Taylor series with respect to delta x, out of which we can probably solve for f prime, because it's here. So far, so good. Let's try doing it. So we want our f at xk plus delta x. In the Taylor series, this is going to be f of xk, reference point, plus f prime of xk delta x plus further terms. In here, we have all the components that we need to make that expression there. We have the incremented f, we have the original f, and we want the f primes that we want to solve for. And some kind of error estimate, which we will now make use of. So for Taylor series, we know what the error estimate is. For that approximation, we don't. But the Taylor series will now allow us to get it. So what I'm doing is I'm solving for this f prime, so I'm shifting this over here, that minus that, and I've got the f prime times delta x, and I've got this remainder. Extracting this, f prime xk delta x is that difference plus the remainder. It doesn't matter if the remainder is positive or negative, it's an order of magnitude estimate of the error. We only want to know that it drops as delta x squared. And then if we divide the whole thing by delta x to get the derivative, what was order of delta x squared once we divide it by delta x simply becomes order of delta x. And so what does this mean? This means that this approximation is accurate to this order in delta x, meaning that we don't actually know what this error is, we only know that it drops as delta x. If we make delta x twice as small, so our grid will become twice as fine, if we, for example, put an extra point into here, this expression guarantees that the error will likewise be reduced by a factor of 2. What people do in practical calculations is they start from some reasonable delta x and they reduce it until the answer stops changing. And as soon as the answer stops changing, as you are making delta x smaller and smaller, you know that you have achieved an accurate answer. situation is called convergence. You've seen it a couple of times when you were doing Newton-Raphson solutions to nonlinear equations. When your answer stopped changing after the next iteration, you know that you've converged. That's the right answer. Now, as you can see, this is not a terribly rapid convergence. If you want, for example, 6 decimal places, you would want the order of 6 decimal places on this grid spacing, meaning the order of 1,000,000 points. 1,000,000 points is an awful lot of points. And so nobody actually in practice uses an approximation that is as, let's say, straightforward as this. Well, let me show you something else. Let us estimate the derivative of xk, not like this, but let us do the following. In here, we have f of xk and f of xk plus 1. There's also somewhere here f of xk minus 1. And what we will do is we will estimate the derivative here as a difference between this and this divided by this interval, which is 2 delta x. So what it will be is f of xk plus 1 minus f of xk minus 1 divided by 2 delta x. Notice the difference with this. This is xk plus delta x, so this is xk plus 1. This used only one point, which was forward of the parent point. For that reason, this is called a forward finite difference. This, when it calculates the derivative at the point xk, it uses the point after and the point before. Such as it is symmetric with respect to the point of interest. This is called the central finite difference. Let's take a look at the accuracy of this. If we have f of xk plus 1 is xk plus delta x. So that is f of xk plus f prime of xk x plus f double prime of xk delta x squared over 2 plus order of delta x cubed. If we look at the other point, f of xk minus delta x is f xk minus f prime of xk delta x plus f double prime of xk delta x squared over 2 plus order of delta x cubed. You can now see why I was torturing you with Taylor series, because we are using this now. And so if we subtract these two, minus, in the numerator we will have this. F of xk plus delta x minus delta x equals. This will cancel. This will acquire a coefficient of 2, so this minus this, so twice that. 2 f prime xk delta x. This term of the order of delta x squared, which was dominating our error previously, will also cancel. They've got the same sign, and we will have something of the order of delta x cubed. Now, if we divide both sides by delta x, we will obtain exactly this. So notice that's the forward point, that's the backward point, 2 delta x is here. Once we divide this by delta x, we will get z prime, and this will become the order of delta x squared. So the error here is order of delta x squared. This is extremely important. When we make the grid finer, let's say by a factor of 10 times more points in here, the accuracy of this expression improves by a factor of 10. The accuracy of that expression improves by a factor of 100. Very big savings on a practical computer. Because normally you need, I don't know, to about accuracy of 21%. So 1 in 1,000, 1 in 10,000 maybe. For that you would need 10,000 points in some circumstances. For this you would only need 100. For what is, by the looks of it, a fairly cosmetic difference. We have not used the forward finite difference, we have used the central finite difference. And so this is how these derivatives are estimated in practical calculations. I would say realistic things that I'm using in daily practice begin at this central finite difference, and there are methods which are of the order of accuracy of delta x cubed, delta x to the fourth, and so on. But in order to get them, you need to engage the points which are further forward, so xk plus 2, and further backward, xk minus 2. So these are more complicated, but they are also more accurate. And this is how numerical differentiation happens in all modern computers and all modern numerical calculations. One important point here is to note that noise makes numerical differentiation unstable. So make sure that your function is actually a reasonable degree of noise before you differentiate. Alright, so this was how we differentiate. Let us now think about the other things that we have to commonly do, and this is to solve ordinary differential equations. And we would have something like this. F prime of t, for some time-dependent process, will be equal some function, we don't know what it is, it's well behaved, of f and of time. So for example, in mechanical kinetics, the concentration derivative as a function of time will be some function of the current concentration, linear, quadratic, cubic, depending on the order of your reaction. And perhaps something is coming into the reactor and coming out of the reactor. This will be your time dependence in there. So this G depends on F and it depends on time. And we were solving this analytically fairly successfully. And you've also seen situations where these are systems of equations, so F is vector valued, and things become horribly complicated. So particularly in situations like the Lowson-Zhabotinsky reaction, which is actually a sequence of many reactions, where G is nonlinear, then these equations don't even have analytical solutions. And so we are in trouble. In which case, what is what Belousov to do? Well, he would have to use that. Imagine that in the knowledge of this, we are trying to solve the equation numerically. Well, we can actually replace that with a finite difference approximation. So let us do that. It will be f of t k plus 1 minus f of t k divided by, and we will give this grid stepping a name. It will be h, just a difference between the time points, time step, if you like, equals. And here we have two possibilities. We can give it g at the current time point, or we can give it g at the next time point. So let's give it g as the current. G of f of t k and t k. Let us think about this. Previously, we had this, and we didn't know what the function was. And so we could neither evaluate the left-hand side nor the right-hand side. It was an ordinary differential equation, and it was hard to solve. Here, everything is a number. Time is a fixed time point. And so calculating g, at least as a function of time, is actually all right. We also know the initial condition, because somebody told us, well, we just know f of t is 0. But this is actually a recursively defined sequence. Why don't we solve it for f of tk plus 1? So multiply that by h and move f of tk over to the right-hand side. f of t k plus 1 equals f of t k plus h g f of t k k. Despite complicated appearances, this is actually a trivially simple object. If we do know f of t0, and we know the t0, calculating g is easy. It's just g of two numbers. G would normally simply be just, for example, f squared for a second order kinetics. So if that's a number, if that's a number, then that's a number. We know the time step, we know the initial condition, and so from f0, t0, we get f of t1. From that we get f of t2, and we move on. Let me demonstrate that in practice. That is our concentration as a function of time, and this is our time, and our a prime of t is minus ka. The function g is particularly simple. Then a of t k plus 1 will be a of t k minus time step h k a of t k. If we begin here, that's our time 0. This is our a naught. A naught minus, so if this hk is a number, minus a fraction of its current value is the next value. The third value will be the second value minus a fraction of the second value, which is now smaller, and so this interval is reduced. Third value is the second value minus the fraction of the second value. We are subtracting a fixed fraction every time. Is the familiar exponential decay, except it will be discretized point by point, because at each point we are subtracting the fraction of what we currently have. That's basically the definition of the process, like radioactive decay. So we've just solved a differential equation numerically. Notice how this will translate directly into situations where the function here is vastly more complicated. It could be some horrifying chain of chemical reactions where that's a kilometer-long expression. Solving such an equation analytically we would have no hope of doing. However, solving it numerically doesn't actually become any harder. You simply have to calculate a slightly bigger function of slightly different numbers at every step. And so such methods are immensely powerful. You can do them in multiple dimensions as well. So here we have time, and our a was a scalar. In principle, we can have time, and our a could be a cube of numbers. For example, the aerodynamic pressure field around an airplane, or it could even be a cube of vectors, so a four-dimensional object, in which case each vector would be velocity vector, for example, around some wing or whatever, where the air is moving. So this is how to estimate derivatives, and immediately once we've learned how to estimate derivatives, we get a method for solving ordinary differential equations. This basic method, which uses just the forward finite difference, has a name. It's called Euler's method. More specifically, this one's called explicit, because we get an explicit expression for the next point as a function of the previous point. Remember the choice we have made. We have used the current point here. If we use the future point here, we would have the implicit method, in which case this will be k plus 1, and we would have to solve a at each point, but that method tends to be more stable. But these are technicalities, right? Much like we have multiple ways of estimating derivatives, we have multiple ways of writing this expression in terms of the pattern of the points that we use, how we evaluate the function on the right-hand side. So books this thick are written on numerical methods, and this is what we actually use in chemical practice. when we are dealing with such things. Let me give you a more direct example. This one's from physics. An electrical oscillator, so just a circuit, which you may remember from your school physics course. Something like that. So capacitor here and an inductor here, with perhaps a resistance in the chain. So if that resistance is R and this capacitance is C and this inductance is L, then if we do have some current in this, so for example if the capacitor was initially charged, then you know that this thing will oscillate and these oscillations will decay. And after you go through a lot of physics of what exactly is going on here, you end up with the following differential equation for the current in this circuit. d2 by dt squared I of t, so second derivative of the current, plus resistance over inductance, d by dt current, plus 1 over inductance times capacitance equals 0. That's a pretty horrible differential equation, not only because it's complicated, but because it is a second order one. I didn't tell you how to solve them. This is the subject of the next semester of this course. So if you are staring at this equation, essentially with the amount of knowledge that you have on how to solve them analytically, this equation is insoluble. However, it contains derivatives, and we know perfectly well how to estimate derivatives. Well, d2 by dt squared is just a derivative of a derivative. What we need to do in here is to estimate. So, let's estimate the first derivative. It will be I of t k plus 1 minus I of t k over h. That's the first derivative. And of course, derivative of a derivative will be that minus I tk minus I tk minus 1 over h over h. So we've estimated the derivative on the right and a derivative on the left. We subtracted these derivatives and divided by the h again. That's an estimate of the second derivative. Plus r over L d by dt. I, let's take the central derivative here. H plus 1 minus I minus 1 over 2h plus 1 over LC I tk equals 0. Well, what was previously a differential equation actually became an algebraic equation for the values of the current on that grid. What I will do now is I will do the following. I will denote it like that. So ITK will be just IK, k's point in the grid. What we have here, therefore, is IK plus 1 minus 2 IK plus IK minus 1 over h squared. This is a finite difference estimator for the second derivative. And as you can see, it's got dt squared in the denominator plus r over L ik plus 1 minus ik minus 1 over 2h plus 1 over LC ik equals 0. Okay, what can we take out of this? Well, we can actually solve this for ik plus 1. It's here, and it's here. And once we do that, we will obtain ik plus 1 will be some function of ik and ik minus 1. And that function will be arithmetical. This is again a recursively defined sequence. If we know the current at the previous 2 points, we can calculate the current at the future point. And this is done in your handout. Once you plot that solution, it will look like this. That's 0, and that is our current, and this is T, and it will oscillate, and it will decay. And it oscillates because of the inductance and the capacitance, and it decays because of resistance. So the characteristic time, I think, will be, where is that equation? Over there, L over R, and the characteristic frequency will be 1 over LC, and then you have seen it all in the undergraduate physics. What that picture in your handout also illustrates is the dangers that such numerical methods have if they're not used judiciously. If we either make the time grid that is too rough, or we use certain types of finite differences that are called unstable, so for example when the function is noisy and so on, what will happen is that our solver will be accurate at the first couple of points, and then it will start deviating from the true answer, and the deviations will become bigger and bigger, and eventually they will exceed the capacity of the computer to store numbers, so it will blow out into infinity. This is called instability. We have no time to discuss instabilities. Essentially, the books will tell you which schemes are stable and which are not, but you have to simply be aware that some numerical methods are more accurate than others because of all these rounding error arithmetic and because of how they interact with the numerical capacity of the computer, which, as you know, is 64-bit precision, which is not infinitely precise. It has a finite accuracy. And so, for example, rounding errors of that finite accuracy can sometimes lead to instabilities. So I will simply mention that such things exist, but we absolutely don't have the time to discuss them. So the bottom line in here is that once we know how to calculate derivatives on grids, we necessarily know how to solve ordinary differential equations on grids. And this is actually a lot easier than it is to solve them analytically, which is why we're doing it every day in chemistry. So people like Richard Whitney never even start a synthesis these days until they've done that to convince themselves that the molecule they're trying to synthesize actually exists and is stable. For that you need to solve Schrödinger's equation. This is how it's solved. The final brief mention that I will make is, of course, these methods that we have for differentiation are also applicable to integration, in which case we need simply to sum up the areas of these rectangles. You may remember the Riemann definition of the integral that we had. It was the sum over all rectangles like that, and for example like this, so this shouldn't be shaded. And this is clearly an approximation because you are missing all of these corners. It will be a lot less of an approximation if you are calculating the area of trapezia instead. And so the approximation with rectangles will have one order of accuracy, but the approximation with trapezia will have another order of accuracy. And if you follow the exact same arithmetic that we had with Taylor series just now, but you do it for integration instead, what you get is the following. Just find out the trapezium rule. So integral from A to B, f of x dx, where A and B is some interval, will be at the most simple level just the Riemann sum. K to 0 to n minus 1, where n is the number of points, f of x, k delta x. So we simply take the value of the function at the start of each interval, and we multiply it by the width of that interval, in which case the element of the area is a rectangle, and this is why this is called a rectangle rule. As you can see from the presence of these corners is not terribly precise, and so the accuracy here is actually again order of delta x. It converges really slowly. If we decide to use trapezia instead, we recover all of these lost little corners. As you can see, piecewise linear approximation in here would be considerably closer to the function than the rectangles. And so the accuracy will improve. So this was rectangle rule. An improvement is the trapezium rule. A, B, yes, these the handout serves sum k0 and minus 1 f of x k plus f x k plus 1 all 2. So you can imagine the area of this trapezium is determined by the midpoint between these two functions times delta x, and this has much higher accuracy. This has cubic accuracy, order of delta x here. So if we have a grid and we integrate with the rectangle rule, if we give it 10 times more points, this will become 10 times more accurate, this will become 1,000 times more accurate, at the cost of including an extra point. So it clearly pays to think a lot about such things. This is called trapezium. Finally, if we were to be really careful and we were to take these points and actually use an interpolating polynomial, and I told you exactly how to build interpolating polynomials a few lectures ago. Let us say we will interpolate this with a quadratic function. So we do something like that. This is our quadratic function. And then, of course, once we know the analytical expression for the function, we can integrate this analytically. And so if we approximate this area as an integral over the interpolant, because the interpolant comes very close to the function, the accuracy improves further. I will not write the fairly extensive expression for it here, but if you actually copy it from the handout where it is given, the accuracy is order of delta x to the fixed. So 10 times finer grid, 100,000 times more accurate. This is called Simpson's rule. Alright, so summary for today. Real chemists never do things with pencil and paper anymore when things come to mathematics. This has been left behind in the 1960s. Realistic time pressures, realistic economic pressures, the availability of cheap computers, and the fairly terrifying cost of making a mistake means that we are stuck with digital computers. As soon as we are stuck with them, we have to manipulate functions on finite grids, we have to differentiate them, integrate them, and solve differential equations on finite grids. This is how you do it. You will see, if you decide any serious software package, derivative estimations that begin at simple finite differences. Usually they're a bit more accurate than that because they use bigger point patterns. And so normally I'd say order of delta x to the fourth is where it starts being production grade. So more complicated equations than that. But essentially these are just differences between the nearby points with pattern somehow and divided by the corresponding delta x's. As soon as we have derivative estimators, we can plug them into finite difference expressions for differential equations. This gives us solvers for differential equations. This is how every equation is now being solved in real industrial practice. And of course, as soon as we are done solving, if we want some total concentration across the sample, we need to integrate that on that same grid. And these are the various different integrals. The rectangular rule comes straight from the limit definition of the integral, much like that came from the limit definition of the derivative. And in exactly the same way, it isn't terribly accurate. And so you can start thinking about that and starting to interpolate the various grids in there, and then you are integrating them to higher and higher accuracy. That's all I have to say.